Welcome to part 3 of today's lecture. And in this, we're going to look at the reality that unlimited exponential growth is unsustainable. So we're going to talk about what limits population growth and what happens when a population exceeds its environment. So we looked at the robins and established that in 20 years, they could exceed 500,000 robins given their ability to reproduce. But that's very unlikely to happen because of mortality and because of a limited environment. And that limited environment has a cap on it that we call a carrying capacity. So we use, for most populations, we use models that include a carrying capacity, and we use the variable letter K to indicate the carrying capacity, and it represents the maximum population size that the environment can support over a long period of time. So if we look at population growth and we look at our exponential growth, we saw that it increased at an ever faster rate over time. But if there's a carrying capacity in that population, a limit on what the environment can support, then what we might expect is that the population will go up toward that limit and level off. Now the question is, does it go right to the limit and then level off, or does it do it gradually? And what we see with that logistic growth model is that the population will start to slow down in its growth as it gets closer to the carrying capacity and eventually level off at the carrying capacity. And again, this is called logistic growth as contrasted with exponential growth. So now we want to think about how can we create a model for logistic growth? How can we create an equation that will allow us to plot this out? So let's look at it in detail. Early on in logistic growth, the growth rate is very rapid. It's essentially almost identical to the growth rate you would see with exponential growth. But at a certain point, it hits an inflection point and begins to slow down in its growth rate. And eventually growth goes to zero when it gets to the carrying capacity. In fact, if it overshoots the carrying capacity, it will actually have negative growth and eventually settle down at the carrying capacity. So this is called the logistic growth model, and it uses the similar variables to what we used before, but it adds in the carrying capacity. And what happens in the logistic growth model is the per capita rate of increase declines. So this is the rate of increase per individual in the population that will decline as you get closer to the carrying capacity. And so we need a term in our equation that allows us to model that. So what we start with is we start with the exponential model, and then we add an expression that's going to reduce the rate of growth as n approaches k. And we see that here. So we have our equation of R max times n, and then we multiply it by this term, k minus n divided by k. And what you'll see is that k minus n divided by k is impacted as the population increases, and it will change the per capita rate of growth in the population. Okay, so let's go through and model this again. So here's our equation again. R max times n times, in parentheses, k minus n divided by k. Again, n sub t plus 1 is going to equal to n sub t plus that delta n delta t. And we have to calculate two pieces in this equation, R max times n and then k minus n over k, and multiply those two together. Okay, so there's our equation. There's our n sub t plus 1 equals n sub t plus delta n delta t. So let's get started. And we're going to use here n sub t equal to 500, R max equal to 0.5, and k equal to 1,000. If we map out the equation, it looks something like this as we put it into, say we're going to try to put this into Microsoft Excel or something like that. So if we take this R max times n, it's the same as we did before, equals 500 times 0.5, so 250. So that would be your growth rate if you didn't have the k minus n over k part. but we need to multiply by the k minus n over k. So let's figure that out. K minus n over k is 1,000 minus 500. So we have 1,000 for our carrying capacity minus our actual population of 500. Calculate that and then divide that by the carrying capacity 1,000 and we get 0.5. So now we're going to take this 250 that we got for the first part and this 0.5 and multiply them together to get the growth rate is going to be 125. If we look at that growth rate of 125 and we add that to our original population of 500, we get a new population at the end of the time period of 625. Now let's contrast that with the growth that we had with the exponential growth rate. So with exponential, using these same numbers, but not using a carrying capacity, we had growth from 500 to 750 in that one time period. With logistic growth, what we see is our population its growth was from 500 to 625 in that same period. So it grew less because the population essentially at this point is about half of the carrying capacity. It will have half of the growth that the other that the exponential growth equation would give us. All right. So we can see that the population is still increasing, but it's increasing at a slower rate as it gets bigger. So we can look at this again. Our two growth equations and where they diverge. And you get that leveling off at the carrying capacity. Now, if we want to look at this, we could map, this is the exponential and logistic growth rates for the exact same equation, one with an R value of 1.0 and a carrying capacity of 1,500. And what you see is that initially the exponential growth is growing the logistic growth is growing pretty similar to the exponential growth, but then it diverges and starts to slow down. Okay, so let's think about this. If we take a look at this and we have the variable n, our actual population, and it gets closer to k, it gets bigger and it's approaching k, what happens to the term k minus n over k? So let's start off with doing a calculation of k being, with k being 1,000, but n being small. So n is not approaching k at this point in time. N is far away from k. And so let's do this with n equals 250. And what we get if we do k minus n over k, 1,000 minus 250, divided by 1,000, we get 0.75. We know that if we have n of 500, so now we're getting bigger, we get a k minus n over k equal to 0.5. Now, as we approach k and we get an n value of 750, if we calculate k minus n over k, we see that we have a growth rate, a k minus n over k term now of 0.25. So k minus n over k went from 0.75 to 0.5 to 0.25, and when n equals k, it's going to be 0. So we can see that as as n approaches k, k minus n over k becomes smaller, but growth shouldn't increase. So becomes smaller, and growth decreases. And this is what we have for an answer. Okay. Now in lecture, what we're going to do is we're going to look at both exponential growth model and logistic growth model, and we're going to look at them for the Upper Peninsula of Michigan and the wolf population there. So up till now, we've been talking about wolves on Isle Royale, but in this case, we're going to talk about the wolf population in the Upper Peninsula of Michigan and study how that population has grown over recent years.